Hello everybody, today we're gonna have a quick tutorial on how to use Vivado software to create a design module using Verilog. Regarding how to install it, please look up on the installation manual and tutorial that we uploaded on Canvas for you guys. So just a quick note is before you do anything with Vivado, before you install anything with Vivado, make sure you have at least 60 gig of memory in your disk, because it's gonna take a lot of memory in the disk space. I'm just gonna say hello world. Okay, so this is my hello world Verilog RTL project. I'm gonna keep next. In this page, technically you wanna put in whatever board that you are using in the class. So I think it's this one, so I go next and finish. So in this hello Verilog, I'm gonna add source, create design source, create file. I'm gonna call it test1. Okay, finish. Okay, yes. Waiting for the file to be created. After that, go here, and you see that once you create a design source, that design source will be imported directly into the simulation. So that's quite convenient. This is my I'm gonna call this one my design module. Okay, so what am I gonna create here? So let's have an example. So I have this example here, and this is created by a software called Logically. It's a paid software, but the demo is free online, so you guys can try it out. It's quite fun. You can control your input, and you can have the output respond accordingly. Demo is quite simple. You can drag and drop a few toggle switch, light bulb, a few gate, a few flip-flop. So it's quite a useful tool in my opinion. So here I'm gonna open my text editor. Okay, so in this pseudocode, what I want to create is I want to treat this thing like a black box that take in this input A, B, C and produce the output D and D. So I think what I'm gonna do is have to declare input and output of A, B, C and D, E. So input A, B, C, output D, E. Also, I have a few intermediate pin, right? So it's kind of like I have this AND gate here that take in some input that feed into another gate. So I'm gonna also define those intermediate pin. Now I'm just gonna define them as wire W1, W2, W3. So that's my plan. Then what I need to do next is I need to figure out how to do mapping of input and output. So in this example, this is what I usually do. For example, for D, if I want to map from D to the input, from output D to input, I'm gonna start from here. I'm gonna see what gate I see first. I see a, what's that called, a NOR gate. So I put a NOR, and this NOR gate taking an input of A and B, right? This NOR gate taking an input of A and B. I mean, sorry, of other two AND gate. Sorry. So this two AND gate is here and here, and this two AND gate taking all the input of A and B. And this AND gate take input of B and C. That's what I'm putting here. I put the two AND gates in there. So I do exactly the same thing for E. I see that coming the output coming from an XOR, so I have an XOR here, that EXO is from 2 AND gate. One AND gate is from A and C, and another AND gate is from B and C. Okay, so how can I implement that? I have two solutions to do this. The first solution is you can use the keyword assign. So you can assign W1, W2, W3 for a certain pattern. Then you can assign D and E. Or you can actually just map the whole thing directly. So if you have a logic function of D and E written in terms of A, B, and C, just write it down. So this is one way. Another way that I want to do in the tutorial today is use the built-in function in Verilog. So in Verilog, technically what you're doing right now is you are writing a function in terms of module. So Verilog already have some built-in gate function or built-in gate module that you can actually use and implement. So the gate module has a convention of input, then the rest of them are output. So this is what we're gonna do. So let's say first I want to I want to describe this gate, right? So I'm gonna call this one gate N0, N1, and N2. So this one is output of W1 and taking the input of A and B, and you see the syntax in here of W1 and output of A and B. Likewise, I'm doing the same thing for W2 and W3. After mapping W1, 2, and 3, now I can after mapping W1, 2, and 3, now I can map to the output of D and E, which I feed W1 and 2 to the NOR gate. So I use the function NOR. Remember that this is the function, or this is the module. This is just the name. I can just put in like funny 0 and it still work. Okay, so yeah, this is, you just need to give a name for this. Anyways, after doing all of that, yada yada yada. Okay, this is my test module, right? So what I want to do is now you just write that in here. So in the test module, you want to put in the pattern for input and output. Let's say in this case, I kind of flip it around a little. I do input first, and I do output. Then I declare input A, B, C, and I want to have my output to be D, E, and I just copy and paste that entire block of code in here. Okay, and you can see that I'm actually currently have an error because I didn't declare the wire W1, 2, and 3, so I'm going to put in wire W1, W2, and W3. So now my code should be relatively error-free, I hope. After that, you want to add source. Now you want to add your test bench, which is called the simulation source. You create file, you're gonna call it test1 tb convention for test bench. Okay, finish. Okay, yes. Now in the sim1, the simulation source, you're gonna have another file called test1 tb. And this one, let's just delete all of this because you don't actually need those. I'm gonna call this my test bench. Okay, in this one here, you want to delete all of this. What you want to do is you want to create registers, and this is where you put the input. You want to create a wire, and this is for the output. So I don't know how to explain this, but just imagine this is kind of like a temporary variable that your simulator is gonna use to run your simulation. So instead of using the keyword input and output in the test bench, you need to use registers and wire. So now let's create some temporary registers and wire. I'm gonna call it TA, TB, and TC. Semicolon, and for the wire I'm gonna call it TD and TE, and this is more of my output. Okay, So now I have some wire, right? So I can plug it in my test module, which is called test 1. So I call it test 1. I'm gonna name this module unit under test. Now I'm gonna plug everything in the exact order. So if you see in here, I'm trying to plug in everything in A, B, C, D, E order. So I'm gonna do exactly the same thing. A, B, C, D, and E order. Okay. So now I finished that. Now I want to initialize my test pattern. Okay. So one way to do that is you can just go and you can set I think you can set TA equal to 0 and you can TB equal to 0 and TC equal to 0, and you can just like wait for 100 nanosecond, then you do something else. You can do something else, right? So let's say 1, 1, 1. Okay, so this should work, right? But what I'm gonna do is I'm gonna try to do a little bit different in here. So I'm gonna create a I'm gonna create a 3-bit bed registers. Okay, I'm gonna initialize that to 0. I'm gonna make a for loop in here. So for I from 0 as long as I is less than 8, increment I by 1 every time you get through the loop, and you want to begin describing what is going inside the loop in here. So in order to do that, you go TA, TB, and TC, and you want to set this one equal to I. Now every time it goes through the loop and did that, I want to wait for 100 nanosecond, and I think that should be my test bench if I didn't make any error. Okay, I is not declared. Maybe here. Okay. Yep. Oh, I think, yeah, I just make a stupid mistake. It have to be 20. Okay, yeah. So save that. that was okay. I think save, updating. Now I think you can run the simulation. I hope nothing wrong will happen. Okay, so in here you can see your simulation. Okay, so you click this button, you can zoom out and you see. So it's run from, let's say, yeah, I can vary my input. What did I do for my test pen? Run from 0 to 8, right? Yeah. Somehow it get looped over again. Anyway. Yeah. Anyway, so you can see I can loop everything in that order. Okay, so 0. I'm gonna move this. So I can 0, 0, 0, 0, 0, 1, and so on until 1, 1, 1. Okay. So let's sanity check to see if actually we have everything correct. Let's test this input 0, 1, 0. So the output should be D equal to 1 and E equal to 0, right? So how can I do that? How can I actually do that? I put this up and I'm gonna move like this. Maybe I'm gonna move this one here. Okay, hopefully you guys didn't hear that. I need to eat something. Okay. All right. So let's test the pattern. What do I have here? I have 0, 1, 0. Should give me 1, 0. Okay, that's correct. Let's test 1, 0, 0. I should have. Oh, so I see there. So I make a mistake, right? So I figure I make a mistake, and that mistake was this one was actually not an AND gate. This one was a NOT gate. So by doing this, I figure out I make a mistake. So an AND gate, not a NOT gate. So I'm gonna come back. I'm gonna fix NAND. Okay. So after this, I figure out that okay, this mistake is fixed. So what I'm gonna do is I'm gonna save it. So I can run the test bench one more time. So I come to here. Nope, I don't want to come to there. Source test bench. I'm gonna run the simulation one more time. Okay, so we're gonna find that 111 110 again. So now it's correct. Okay, so let's pull logically up. Okay, let's test one more pattern to make sure that we have everything correctly. Oops. Okay, let's test right here. So this is 101, and you should have. And if I test 110, 110, so we have 01. Correct. All right. So everything is good. So now your simulation is good. What do you do next? There's some feature is called the analysis. So if you click here, open elaborate design, hit OK. So it kind of run your code, and in this feature, you can actually see your schematic that Verilog, like that Vivado interpret from your code. Okay. So let's wait for everything to run. So you see here, it read that. So it reads that there's an AND gate. Okay. So instead of an AND gate, instead of an AND gate, it's actually run through an AND and inverter. So it's an AND. So it's quite similar. It's actually similar to what we had before, right? What we have in Kate. Not in Kate, in Logically. So you can pull it up. You can compare for yourself. Anyway, so in here, what you do next is you now you're gonna do the mapping of your input and output to actual board. So I'm gonna pull up some picture on the internet. Basis 3 Actic 7 FPGA board. I'm gonna find some image. Okay, so I have this image here. Nope, I wanna find like a high resolution image. Or IO port. Or here. Okay. Okay, so you see that there's some label. You see that there's some label on these pin, right? So each of these input switch or these LED here has technically a name to it. I want to find a better image that I can use. So for example, this LED is called L1, this LED is called P1. So I want to map D to this LED, and I want to map E to this LED here. So what I'm gonna do is I'm trying to zoom in this picture. It's quite difficult to see, but anyway. So now, 1 second there. So in here, you see this table, right? If I go to package pin, now the output, I can name this one L1. I can name this one, what's that called? P1. Okay. So now this switch, I think is is that V2? This is V2. This is T1, B1, U1. Yeah, so that's something you can do. So you can map to this input ABC to this switch, and this switch, and you can map the output DE to this LED and this LED. So that's something you can do using Vivado. Okay. So after you do all of that, right, you finish off the mapping, you can synthesize your circuit. Okay, so it will create a file called design constraint 1. So file name hello synthesis. Okay, so I think my synthesis is ready. Okay, so if I come here, constraint, okay, so you can see the port mapping in here. Okay, then this is my synthesis report. If you click on report, you can have the synthesis report. Okay, and the last thing to do is right now run implementation. No, I don't have a board right now to run the implementation. I want to open the synthesis design when this is finished. So you see, once your synthesis is complete, it will say this. Yeah, so you see, and you hit open synthesis design, so this is kind of like what is gonna happen in your FPGA. So like what gate will be mapped. So it's kind of cool to look at this. Yeah, so this is the actual design that come out from your Verilog code in here, and this is the report. So you can get access to that easily from this table in here. And one last thing is you can generate bit stream. So you can click on this, say yes. I'm just gonna launch localhost. Yeah. So you can. So what bitstream does is, I don't know if I can have it in here. But this is probably the end of the tutorial because I don't have an FPGA board here. So bitstream is technically a binary file that you will input that into your FPGA, so that your FPGA will be mapped into this design in here that you just made. Once you have the hardware ready with you, you can just you can open target, you can choose what you can hit auto connect if you have a board, but this case I don't have a board, so no hardware target was open. So I'm just gonna turn it off. But once you have everything connected, just hit auto connect and you can run your bitstream. Okay, so that's it for today. I hope you guys understand how to do this, and I wish you're successful in your lab. Thank you very much, and I hope you have a good one. Bye.